Imagine this for a second. You are not driving on a bridge, you're driving on a giant steel guitar string. Pluck the string right way and the whole thing will hum with vibration. Hit it the wrong way though and it literally tears itself apart. The Golden Gate Bridge has two main cables. Each cable is 3 feet across, and each one is made up of 27,572 individual wires strewn across the whole span of the bridge. Each one of them is pencil thin. If you laid them end to end, the wires would wrap around the entire planet 3 times. That bundle is what is holding you up the next time you cross a suspension bridge. Here's the part nobody tells you in school, though. Almost every bridge you've ever crossed is held up by being pushed from below. Most bridges consist of beams, arches, trusses, all of them pushing against the structure of the bridge, making it hold its shape. A suspension bridge works totally different. It hangs from a series of cables and suspension ties. The deck is dangling from cables. The cables are draped over towers. The towers shove their weight straight down into the rock. It is really pretty crazy if you consider this bridge has both a pull system and a push system built into it. That's the paradox. When a chain hangs with nothing on it, gravity is just pulling its own weight. It makes a curve called a catenary. Now hang a roadway off the bottom of that chain. The shape changes. It flattens out toward the middle. It becomes a parabola. That tiny shift, though, amazingly, that's the entire trick. A parabola helps spread the weight evenly across the cable. Every inch of cable is doing exactly its fair share of work. If you got the shape wrong by even a little, the cable would bunch, causing a major failure in the design. The weight of the bridge would tear itself off the towers, causing it to collapse. Principle Ujro 1. Every part of this thing is fighting a different battle against physics. The towers are getting crushed. The compression pushes hundreds of thousands of tons, squeezing them straight down into bedrock. The cables are getting stretched to their max. Thousands of pounds of tension are pulled taut between the anchorages. The bolts and joints are dealing with a force called shear. Different parts are trying to slide past stuff that was originally designed not to move. The deck itself, though, it has to resist several different forces we have already discussed briefly. Torsion, twisting, being stretched and squeezing. All 4 of these forces are being used against the bridge at the same time, forever. If even one of those 4 fails, the whole thing comes crashing down to earth. Principle O2, before you can build a bridge, though, you have to anchor it. These anchors live at the bottom of the river. In the 1870s, the way you got down there was a thing called a pneumatic caisson. It's a wooden box sealed at the top, but it's open at the bottom. They then drop it on the riverbed. Once on the riverbed, they pump compressed air into it. The air pushes the water out. Now you've got a dry chamber sitting on the mud full of men with shovels. They dig the soil out from under the box, even as the box sinks deeper. The men have to keep digging. They will eventually hit bedrock. Once they do hit bedrock, the men will fill the box with concrete. This will act as the foundation for the massive bridge. Sounds clever, right? Unfortunately, it was a death trap for the men. However, here's what nobody knew yet. When people breathe pressurized air for hours and then come back up, nitrogen bubbles form in your blood. Your joints lock up. People become paralyzed. They called it caisson disease. We now call it the bends. Workers building the Brooklyn Bridge were dying of it. Nobody understood why or what was happening yet, though. The man in charge of the construction was named Washington Roebling. He went down into the caisson himself one too many times. It unfortunately also ended up crippling him. He spent the rest of the project watching the bridge get built through a telescope from the window of his bedroom across the river. His loving wife Emily walked to the worksite for him every day, delivering his orders to the crew. The Brooklyn Bridge basically got built because a wife became a structural engineer. Principle 03. Once the foundation is in, you have to put a tower on top of it. A modern suspension bridge tower is taller than most skyscrapers. The Yi Sun Sin Bridge in South Korea, 270 meters of solid reinforced concrete. How do you pour concrete that high without it cracking at every floor? You don't stop pouring. It's called slip form construction. You build a steel mold around the bottom of the tower. You pump concrete into it nonstop. The mold slowly climbs upward, centimeters per hour, for weeks. The concrete behind the mold cures as it goes. When you finish, the entire tower is one solid piece of concrete. No seams, no weak joints, just raw strength. Korea poured the Yisun-sin pylons on a deadline measured in months, not years. Principle 04. At the very top of every tower is a thing called the saddle. It's a chunk of cast steel the size of a car. The main cable lays in the saddle like a rope and a pulley. Here's the part most people get wrong. Wow. The cable is not bolted down. It's allowed to slide. It's allowed to move. If you fix the cable to the tower, every time the wind shifted, the cable would yank the tower sideways and it would crack at its base. So engineers put rollers under the saddle. The saddle floats. The cable shifts when the bridge breathes. This allows the tower to stay vertical forever. Principle 05. How do you actually make a cable that's 3 feet thick? You can't truck it in. It's too heavy. You build it in the air in real time. A man named John Roebling invented this method in the 1800s. You string a temporary catwalk between the two towers. Then a steel wheel rides back and forth on the catwalk, carrying one loop of wire at a time. The steel wheel pulls the wire across. It comes back. It pulls another wire across. It comes back and gets another wire to pull across. For the Golden Gate Bridge, it did this 27,572 times. When finally all the wires are in place, a hydraulic jack squeezes them into a single bundle of wire. You wrap them, you paint them. That's it. That's a main cable. 9 months of work in all the elements. Finally completed just over 300 meters above the water. A century later, somebody asked a heretical question. Why are we building cables in the sky? Why aren't we building them in a factory, then just hauling them to the bridge? That's called a PPWS, prefabricated parallel wire strand. You bundle the wires in a building with air conditioning, ensuring quality control. The work mostly completed by robots. You ship the finished strand to the bridge on a barge. They then haul it across the span of the bridge. They then drop it in the saddle of the bridge. They then call it a day. The job's done. The Akashi Kaikyo Bridge in Japan was built this way. The 1915 Urupuspas and Nakali Bridge in Turkey, Eshtartor, that one is currently the longest suspension bridge in the world, 2,023 meters between the towers. PPWS cuts the on-site work in half. It's really amazing. It also means the most dangerous job on a bridge isn't done up in the air anymore. So we've got the cables figured out, we've got the towers figured out, we've got the foundation figured out. However, in 1940, we discovered we had not figured out the wind yet. There was a brand new bridge in Washington State called the Tacoma Narrows. It consisted of a beautiful, slim, modern design. It opened in July of 1940. By November of the same year, it was at the bottom of the bay. What happened, you must be wondering? A 40-mile-an-hour wind hit it. When the wind roared over, the deck started to twist. This is called torsion. The same force that wrings out a wet towel took down a bridge. The twist got bigger and bigger and bigger until it could not sustain itself any longer. The bridge was 4 months old. However, now it was gone, reduced to a pile of rubble. Engineers had built the bridge to handle the weight of the wind. They just forgot that wind also takes different shapes. After the Tacoma Bridge fell, engineers stopped designing decks like rectangles. They started designing them like airplane wings. The Severn Bridge in England in 1966 was the first one with a streamlined box. The design was girthier, smoother, closed, and more importantly, aerodynamic. The wind flowed over it like a river, not into it, but for spans over 2,000 meters, even that wasn't enough. So they cut the deck in half. They came up with a new design, this one with 2 boxes and a slot down the middle. The wind blows over the top of the box, under the bottom box, and through the slot in the middle. The pressure is now equalized. The vortex never forms. The deck never twists. Contortion never happens. That slot is what makes the world's longest bridges possible. There's a side effect to all this aerodynamic work, though. Sometimes the bridge sings. In 2020, San Francisco added new slatted railings to the Golden Gate Bridge to stiffen it against wind. The slats worked perfectly. The slats also turned the entire bridge into a flute. When the wind hits a cylinder at the right speed, it creates alternating vortices behind it, spinning eddies, one on the left, one on the right, one on the left. Physicists call it a Riemann vortex street. If those vortices match the natural frequency of the structure, you can actually hear the structure sing. The Golden Gate Bridge hum is a high single tone, audible all across the bay. People in Sausalito sleep with their windows shut now because of the singing of the bridge. The bridge is not broken, though. It's just singing its wind song. Principle, or 6. South Korea has thousands of islands. They needed to connect them together. They didn't have time to build every bridge the old way, though. So they reinvented the process. The deck of a modern Korean suspension bridge isn't built on the bridge. It's built in a factory, 25-meter segments at a time, cast in a controlled environment, cured with no humidity drift, no temperature swings. They then roll the segment onto a barge and float it all the way to the site. A launching gantry, a giant steel arm crawling along the bridge, peers, picks the segment up, drops it in place, bolts it down. The factory is making the next segment while the gantry is placing the last one. What happens to the total project time? It's cut in half. Sometimes it's up to 75% faster. It's not bridge building anymore. It's an assembly line. Principle 07. The factory is just the start. Korean construction firms are putting robots on the cables now. Autonomous machines that climb up to where humans can't safely work. They tighten structural bolts, all while keeping humans safe. The bridges themselves are getting smarter too. Modern Korean and Chinese suspension bridges are built with thousands of embedded sensors, strain gauges, corrosion detectors, wind speed, seismic monitors. Even the temperature is monitored. All of it streams in real time to a thing called a digital twin of the bridge, a 3D model that knows what the real bridge is feeling in real time. The digital twin runs simulations. What happens if a hurricane hits next Tuesday? What happens if a 100-ton truck drives over the deck right now? The bridge knows, sometimes even before the engineer does. So here's where we land. Suspension bridges started as the most reckless thing humans ever did with steel. We hung roads off chains. We sent men into pressurized boxes at the bottom of rivers. We built structures that we didn't fully understand and watched them tear themselves apart in the wind. A century later, we still hang roads off chains. We just hang them from cables made in factories, anchored on towers poured in continuous columns, decked with twin-box girders that breathe, all while it's monitored by a digital twin that feels every gust. The paradox is the same. The bridge is still being pulled. It just knows it now. There's one paradox left, though. What if the next bridge is not above the water at all? In Norway, engineers are designing something they call a submerged floating tunnel. Imagine a road in a tube, 100 feet underwater, held in place by cables tied to floating pontoons on the surface. You drive into a hole, then just disappear under the waves before finally coming out the other side, never having crossed a bridge at all. That's not science fiction. The first one is on Norway's drawing board right now. It's a road that swims. If you learned something from this one, hit the like button. It tells YouTube to show this stuff to other people. Subscribe if you want more engineering broken down the way it actually works. And drop a comment with the most terrifying bridge you ever crossed. I read every one of them. We'll see you in the next video.